Hey guys, Miss Gosling here. In this video, we are going to talk about Hertzsprung-Russell diagrams, otherwise known as HR diagrams. And by the end of the video, you will be able to classify stars by their location on an HR diagram. We will also be talking about how you can show a star's progression through its life cycle using an HR diagram. So let's go ahead and get started. So your IB understandings are that you should understand what an HR diagram is, and your applications and skills, you should be able to sketch and interpret HR diagrams, and you should be able to identify the main regions of the HR diagram and describe the main properties of stars in those regions. Now, one thing that's kind of nice is we've actually already talked about most of the regions and most of the properties of the stars in different regions. We just haven't talked about where those regions are. So with no further ado, let's talk HR diagrams. So to the right here is an example of an HR diagram. An HR diagram, as you can hopefully see, shows the relationship between the temperature of a star on the x-axis and the luminosity of a star on the y-axis. Now, typically, when we look at luminosity, we are measuring that in solar units. So each number that you see on the y-axis, we want to multiply by the mass of the sun to get the actual luminosity. A couple of other things I want to point out. It is pretty frequent to see at the bottom of an HR diagram the stellar classifications. So if you remember, we talked about how we could classify stars based off temperature and based off of color, and we have letter names for those different classifications of stars. That is often shown on an HR diagram as well. So I want to take a moment to point out the regions on the HR diagram. So as you know, we talk a lot about the different parts of the life cycle of stars. So the main sequence, these are my young and fun stars, are pictured here. So the main sequence of stars tends to start kind of at the top left corner of the HR diagram and then just go down at about a 45-degree angle, ending in the bottom right-hand corner. So we expect for there to be, as you can hopefully see in the picture, a pretty clear mathematical relationship between the mass of the star and its surface temperature. Anything not on the main sequence is at a different stage of development. So my stars on the main sequence will first become either giants or supergiants. We define giants and supergiants as entirely based off of the relationship between luminosity and surface temperature. So the closer we are to the main sequence, the more likely we are to be classified as a giant. When we get farther from the main sequence, kind of up in this very top right corner, that's when we see our supergiants. So a star on the main sequence is going to become first a supergiant or a giant, and that's when it switches from fusing hydrogen into helium to fusing helium into other elements. And then eventually, once it has finished up fusing helium, and once it has finished with nuclear fusion, it's going to go ahead down here and become a white dwarf, as long as it is under, of course, the Chandrasekhar limit in mass as a white dwarf. If it's over, it becomes a neutron star or black hole, which are not pictured on this diagram. So hopefully from here you can kind of see how we would diagram where a star's life cycle takes it on the HR diagram. So you've seen an HR diagram, we've talked about the star life cycle on HR diagrams, but I think one big question is who cares? One thing that's really useful is that we can use HR diagrams to figure out how far away a star is. So just like how we've been able to use the luminosity brightness relationship and the parallax angle relationship to figure out stellar distances, we can also use it to figure out, we can also use HR diagrams to help us with this. So if we're able to determine the spectral class of the star, so that gives us the color and the approximate temperature, and we know its classification, so we know if it's on the main sequence, a dwarf or a giant, then what we can do is we can plot the star on the HR diagram and find its luminosity. Because remember, on my HR diagram, I have temperature on one side and luminosity on the other axis. So if I'm able to look at a star and I know that it is very hot, but not very luminous, if I know it's a white dwarf, then what I can do is I can plot it on my HR diagram, and I can figure out what its luminosity is by just putting it kind of in its general region on the HR diagram. I could do the same with stars along the main sequence or stars that I know are giants or supergiants. By plotting its approximate location on an HR diagram based off of its spectral class and its star type, I can go over to my y-axis and find my luminosity. Once I have plotted on the graph and found its luminosity, I can, just like with standard candles, compare luminosity and apparent brightness and use that to determine the distance of the star. So let's go ahead and do an example from an old IB exam. The HR diagram shows several star types. The luminosity of the sun is L sun. Identify on the HR diagram the position of the sun. Label the position S. So we're going to ID where the sun is and label that position with the letter S. Now, when I'm looking at my HR diagram, the first thing I want to do is take a look at what the units of the y-axis are. So if you see here, luminosity is given in units in luminosity divided by the luminosity of the sun. So that means that the luminosity of the sun in that unit is 1. I also know that the sun is going to fall somewhere along the main sequence, which I can see is this sort of line that's at about a 45-degree angle across the graph. So what I'm going to do is I'm going to go ahead, I'm going to look at the luminosity of the sun, and I'm going to draw a little line over to the main sequence. I'm going to go ahead and label the luminosity of the sun S. So what I did was I said, okay, I know the luminosity of the sun is divided by the luminosity of the sun, which is the unit here, must be equal to 1. So I looked at 1 on the y-axis, and then knowing the sun was a main sequence star, I looked at where the main sequence intersected with a luminosity of 1 sun luminosity. And here we go. So let's go ahead, look at the mark scheme. And again, what you'll notice here is we've got this big black oval on the mark scheme. What that means is any spot in that oval would have been an appropriate place to mark the luminosity of the sun. As you can see in my previous answer, I did put the luminosity of the sun at approximately here, which is well within that oval. What I want you to notice, though, is that that oval is a wider range, so you could have gone to the left or to the right of that area at luminosity of 1 on the y-axis, and you would have been correct. So let's go ahead and talk takeaways. First of all, HR diagrams show the relationship between temperature and luminosity. We can use HR diagrams to help us determine the distance of stars, and it's important to know where different colors of stars fall on the HR diagram, and more importantly, where different types of stars fall on the HR diagram. So there you have it, guys. You have officially learned what HR diagrams are, how to interpret them, and how to use them to better understand the stars you see in our universe.